This is a lesson on inverses of functions. So if we happen to have a finite set, some function that has these ordered pairs, all we have to do is simply swap the x value for the y value, or the input with the output is really what we're doing. And so the inverse of this set A, written with this A and the little -1, that's not an exponent, that's the inverse of A, we just swapped our output and our input for each one of those ordered pairs. With an equation, we could have two different cases. One where it's not in function notation, it's just got x's and y's. Well, so here's an equation. We just simply swap the x's and y's, and that gives us an inverse relation. We don't know if it's a function. We don't know if the original one was a function or this one is a function, because it wasn't in function notation, so we just have inverses. Second case with an equation would be that it's in function notation, so it's starting off saying this is a function, which implies that it passes the vertical line test if we were to graph it, and here it is. So this is some function. The first step we have to do is actually write it outside of function notation, so we change that output with function notation into a y. Then we swap our x and y, and because this was function notation, we do need to solve for our y. And by doing that, this was a division, so we multiply by 4, then we add 3, and then we divide by 2. And here it is. We need to simplify that a bit and write it in function notation. So we write it in this function notation. The f inverse of x is equal to this. We could simplify that a little bit more, and this is kind of a nicer, cleaner version of it, but this is perfectly fine. And so this is the inverse of f. We can also look at the inverse of a function graphically. And so we will look at the equation, or we'll look at a graph of some function, and when we reflect it over the line y equals x, we will have its inverse. So this red line is some function that we know of, f of x, and here is the nice diagonal line y equals x. And if we reflect it over that, the green represents the inverse of it, so it's a mirror image over that line. So each one of these points is equidistant to the line. So we have that green inverse function. Here's another function that has a terminal point here. This is where it starts, and then it's an increasing function, and it turns and keeps going up, and this is some function f of x. We have the line y equals x. We reflect it across it, and we get the inverse function graphically. Now, when an inverse of a function, these green, when an inverse of a function, this green one here and the green one over here, when they are also functions, we say that the original function, f of x, the red one here in this case, and in the other one, this one here, we say that the function is a one-to-one function. And what that means is each input and output pair is unique. So the question is, are all functions one-to-one? The simple answer is no. And here's the easiest one to look at is we know that y equals x squared is a parabola. And the inverse of that, which would be to swap the x's and y, x equals y squared, well, that happens to be, as we've studied in previous courses, that's a parabola that fell over in a sense. So we can look at it this way. We can see that the original function y equals x squared, that this is a function because it passes the vertical line test. But this red inverse relation is not a function because it would fail the vertical line test. So what are the tests without having to come up with the inverse? What would the test be if I just had the function itself for it to be one-to-one? Well, graphically, we would just look at just the graph of the function. And if the function passes both vertical and horizontal line tests, then we know that it is a one-to-one function. So here, of course, is our vertical line, and we know that if we take this vertical line and move it anywhere on the graph, it's only going to touch that function in one and only one place. But if we look at the horizontal line, now that fails because it touches the function in more than one location. So for this input right here, it's going to have an output, and this one right here has an input, and its output is the same. So the output is not unique. Two different inputs have the same output. And we use that idea, that two outputs that are the same for, one output that has two different inputs, for looking at it with an equation. And what this is saying is that when two outputs are equal, then the inputs must have been equal as well. So this is actually how we're going to do the test. We set their outputs equal to each other and show that what was put into the function had to be equal as well. So here's an example of that. We have this f of x equals the square root of x plus 2. First of all, we're going to set up as if there's two different inputs, a and b, whose outputs would be equal. So we plug in an a on this side, and we said equal to the other one with a b in it. And now we're going to square both sides. We're going to try to show that a has to equal b. If we can show that a doesn't equal b, then it's not 1 to 1. By squaring both sides, we get a plus 2 equals b plus 2. Subtracting 2, we've got a equals b. That's the only possibility when we simplify this. So therefore, this function is 1 to 1. But let's look at another situation. Look at this function. Once again, we're going to set two different outputs equal to each other. Well, they're going to be outputs that are equal, so they both have the same output. And we're going to simplify this, trying to get to the a. We're going to try to solve for a, so we're going to square both sides. Now we're going to subtract 25. Well, those are both negative, so let's multiply that by -1. And now I've got a squared equals b squared, so we'll take the square root of both sides. But remember, when you take a square root, you get both positive and negative results, which is saying that the inputs could have been equal, or they might have been opposites of each other. And that's not, that means it fails this test, so it's not 1 to 1. It's saying that we had outputs that were equal, but it's possible that the inputs are not equal. They could be opposites. So that would mean that this is not 1 to 1.